welcome to the LINAC Coherent Light Source at SLAC National Accelerator Laboratory. Known for our high-brightness, hard X-ray free electron laser, hundreds of investigators come from around the world to our X-ray facilities to test their brightest ideas. But did you know that most of these experiments also rely on a wide array of optical lasers? In this short presentation, we're going to explore the fundamentals of laser delivery at LCLS, including who we are, what we provide, and how we help fulfill the vision of your experiment.
Optical laser delivery for LCLS experiments is supported primarily by two departments within the LCLS Directorate, the Laser Engineering Department in the Engineering Division, and the Laser Science Department in the Science Research and Development Division. Each department plays a crucial role in facilitating LCLS laser operations. The Laser Engineering Department manages and maintains baseline laser system performance. This includes routine system maintenance and performance checkouts by the Laser Systems Group, frequency locking and precision timing control by the Timing and Synchronization Group, and laser-specific mechanical design, development, and fabrication by the Laser Mechanical Engineering Group. On the other hand, the Laser Science Department serves as your primary resource for scientific integration of lasers to support LCLS proposals and beam times. Here are some of the things you should know about working with an instrument laser scientist throughout the life cycle of an experiment. At the proposal stage, the instrument laser scientist can give you an accurate description of current capabilities and help tailor your request to be technically feasible while also being scientifically viable for your proposed application. Once your proposal has been accepted, congratulations! You and your instrument point of contact should collaborate with the instrument laser scientist to plan, design, and actualize the optical laser aspects of your experiment. A crucial part of this effort is carefully capturing all of your optical laser requirements within the Optical Lasers tab of the questionnaire. Of particular importance are any non-standard requests, such as uncommon wavelengths, restrictive incoupling geometries, or non-SLAC laser sources you plan to bring with you. In all, a well-executed questionnaire enables the instrument laser scientist to create an appropriate laser support plan for your beam time that draws on necessary resources from the laser engineering team and gets everything ready on time. For the beam time itself, the laser science point of contact will assist with the overall support of the experiment, giving you all the necessary instructions on tuning and manipulating the optical parameters of interest, as well as lending their own scientific expertise to the collaboration. Afterwards, they can provide necessary calibrations, documentation, lessons learned, and ongoing support for data interpretation, publication preparation, and follow-up proposals. Now that you know who we are and the role we can play in your successful experiment, let's meet some of our laser scientists as they tell us more about the optical laser capabilities of our labs.
Hi, I'm Matt, and this is TMO.
TMO offers two different interaction points where the optical laser meets the X-ray laser. IP1 has multiple modular end stations like the magnetic bottle and the angle-resolved electron time-of-flight spectrometers. We currently offer the fundamental 800 nanometer 20 femtosecond laser at up to 33 kHz. Our standard configurations include harmonic generation to deliver compressed second and third harmonics of the fundamental, which are typically used for UV photochemistry applications. We also have an OPA and offer tunable near-infrared, which is often used for angular streaking. IP2 houses the DREAM end station, a dynamic reaction microscope for coincidence photofragment imaging. The fundamental laser for this end station is 1 micron, 30 femtoseconds, and also runs up to 33 kHz. We will initially offer second, third, and fourth harmonics, and we use a custom off-axis parabolic mirror to reach a very tight laser focus of around 10 microns. At both end stations, we have an arrival time monitor that tags the single-shot delay between the laser and X-rays to better than 20 femtoseconds. The laser capabilities of TMO are evolving, and the team is excited to work on ambitious experiments, so reach out to the Hutch scientists about your needs.
I'm Giacomo.
I'm Mina.
And this is Rix. Come on in. Rix is a multidisciplinary beamline taking advantage of the new LCLS2 superconducting accelerator, which can provide one of the brightest X-ray beam on Earth. Rix currently features two end stations, QRix and ChemRix, which focus respectively on condensed matter physics and liquid phase chemistry. The experimental techniques of both end stations is resonant inelastic X-ray scattering, also called RIX. For these end stations, we offer an array of laser capabilities to meet the needs of a diverse user community, focusing on offering a broad range of wavelength tunability for ultra-short pulses at high average powers. In ChemRix, we use the high rep rate beam generated by 800 nanometer OPCPA. The fundamental beam can be frequency converted in the Hutch to offer harmonics in the UV spectral range and optical parametric amplification in the visible range. In QRix, we use the output of a spectrally broadened carbide laser at 1 micron, which generate a range of wavelengths from harmonics into the UV range and tunable IR and mid-infrared pulses down to 16 microns. This is a relatively new beamline, so discussion with the instrument team is strongly encouraged to prepare your proposals and experiments. For details about the laser parameters, please contact the laser POC for each end station.
Hi, I'm Matthias Hoffmann. I'm the laser scientist for the XPP instruments.
XPP is the premier experimental hutch at LCLS for hard X-ray condensed matter science. We are highly flexible in terms of both pump wavelength and the X-ray configurations. Our fundamental laser system is an 800 nanometer titanium sapphire laser that can deliver up to 15 millijoule compressed pulse energy into the hutch. We can run either in a narrow band 100 femtosecond or a short pulse 50 femtosecond mode. We have high energy OPAs for near infrared and mid infrared conversion. We can also cover the visible and UV wavelength ranges. A specialty of our hutch is the availability of single cycle or multi-cycle terahertz pulses for high field nonlinear terahertz experiments. XPP will go offline at the end of run 23 in November 2024 and will be down for the year of 2025. XPP will be reconfigured at the end of run 23 for the HE upgrades. We will come back for run 26 with an improved 800 nanometer setup and be operating at 120 Hz for another year.
Hi, I'm Gaurav and welcome to XCS.
The XCS instrument can perform a wide variety of experiments with hard X-rays, ranging from X-ray photon correlation spectroscopy of solid-state samples to liquid phase chemistry experiments using X-ray scattering as well as absorption and emission spectroscopy. The majority of XCS experiments use an ultrafast laser to optically excite the sample. XCS is equipped with a commercial titanium-doped sapphire laser operating at a repetition rate of 120 Hz and delivering 6 millijoules of compressed 35 femtosecond pulses centered at a wavelength of 800 nanometers. The laser can be frequency converted via harmonic generation or optical parametric amplification to generate wavelengths in the range of 260 to 2600 nanometers. The laser focal spot is typically 50 to 100 microns full width at half maximum at the interaction point, and the available pulse energy is strongly wavelength dependent. Motorized control of the laser pulse energy and polarization are also available. Discussions with the laser and instrument teams are strongly encouraged before proposal submission, especially for non-standard laser delivery requirements.
Hi, I'm Greg, and this is MFX. MFX has one of the most flexible sample environments at LCLS, coupled with the most diverse laser capabilities. A native titanium sapphire-based laser system can deliver 7 millijoules of compressed 800 nanometer light at 120 Hz. This system can pump an optical parametric amplifier, delivering tunable laser light from 470 to 2640 nanometers, with shorter wavelengths available upon request. This setup has a time resolution of about 50 femtoseconds. This hutch also facilitates the addition of portable, standalone laser systems. These systems include a nanosecond ND-YAG laser that can deliver 4 millijoules at its fundamental of 1064 nanometers, as well as the second and third harmonics. In addition, MFX also offers a pair of optical parametric oscillators providing nanosecond pulses with a breadth of tunability in terms of wavelength and pulse energy. These lasers are mainly used to pump protein samples, typically in solution or droplets.
Hi, I'm Kurt, and this is CXI. The CXI Hutch's laser system offers femtosecond pulses that can be used in conjunction with hard X-ray scattering to map out structural rearrangement and transformation in photoexcited molecules with femtosecond time resolution, essentially following chemistry in real time. The baseline system in CXI is a commercial 800 nanometer titanium sapphire laser system providing a few millijoules of pulse energy compressed at 40 femtoseconds at 120 Hz. From there, we can generate harmonics in bulk crystals at 200, 266, and 400 nanometers with pulse energies between a few to hundreds of microjoules depending on the wavelength. Continuous tunability can also be delivered via an optical parametric amplifier, which spans about 240 to 2400 nanometers. Available pulse energies vary depending on the wavelength range of interest, but can also range from tens to hundreds of microjoules. In addition to the tunable pump wavelength, the pulse duration of the excitation pulse can also be varied from near the transform limit to picosecond durations using a home-built 2-prism compressor. In addition to the standard titanium sapphire laser system, there are additional roll-up nanosecond pump lasers that can provide longer pulse capabilities with a wide tuning range of 410 nanometers to 2200 nanometers, with pulse durations roughly 8 nanoseconds. Please reach out for any additional details regarding the laser system in the hutch, and we can get the conversation going.
Hi, I'm Nick Chaplin, and this is MEC.
MEC provides the highest peak power and highest energy laser systems at LCLS. A 1 joule 5 Hz TISAF laser system provides high contrast 800 nanometer 40 femtosecond pulses for relativistic laser matter interaction. This laser can also be frequency doubled to 400 nanometers, be operated in an uncompressed mode at 1.5 joules and 150 picoseconds, or be delivered in a low energy, high repetition rate with few millijoules at 120 Hz. Additionally, MEC's nanosecond ND glass laser provides variable pulse shapes between 5 and 35 nanoseconds with peak powers up to 10 gigawatts and a pulse energy up to 100 joules. These pulses are primarily used for shock physics and dynamic compression experiments. MEC also offers a visor laser and a commercial optical parametric oscillator as optical diagnostics. Beam delivery platforms are available for focusing either the short or long pulse beam to target using rapidly installed components. Some of these platforms are incorporated into standard configurations, which are detailed on our website. However, these platforms can be used for non-standard layouts as well. Discussion with the instrument team is strongly encouraged to reach an optimum setup with available equipment in the hutch.
Hi, I'm Randy Lemons. Hi, I'm Patrick Kramer. This is the Ultrafast Electron Diffraction Instrument, or UED. At UED, we do ultrafast laser pump, mega electron volt electron probe experiments in a variety of sample chambers. We use a ultrafast titanium sapphire laser with a main center frequency at 800 nanometers, repetition rate of 360 Hz, with options for lower rates down to single shot on demand. The wavelengths we offer are the harmonics of the titanium sapphire laser, 800 fundamental, 400 nanometer, 266 nanometer, and 200 nanometer. Additionally, we have an optical parametric amplifier, or OPA, that can deliver tunable UV, visible, and near IR between 240 nanometers and 2.4 micron. For longer wavelengths, we can do difference frequency generation to make mid-IR, or optical rectification to make terahertz pulses. Especially for mid-IR and terahertz, some extra effort is required, so please talk to our scientists ahead of time for those type of experiments. The instrument response of UED is around 150 femtoseconds, and we can do pump probe delays of over a nanosecond if necessary.
Beyond supporting the laser operations of today, the LCLS Laser Engineering and Laser Science departments are also committed to a bright future of expanded user capabilities. Such efforts include community-informed improvements to our existing instruments, new off-LINAC laser capabilities for LCLS-centric research and development, and long-term technical support for several major facility upgrades. If you'd like to learn more or voice your interests, please refer to our website for more information and our contact information. We look forward to collaborating with you soon.